Right now, as you watch this video, you're witnessing one of the most spectacular shows in the universe. Above your head, countless stars burn with the fury of nuclear fusion. Galaxies spiral through space in cosmic dances that have lasted billions of years, and the very fabric of reality sparkles with the light of distant suns. The cosmos appears eternal, permanent, magnificently alive. But there's something you need to know about this cosmic light show. It's all temporary. Every star you see tonight will eventually burn out. Every galaxy will exhaust its fuel. Every source of light in the universe will gradually fade until space becomes darker than you can possibly imagine. The universe is marching toward an inevitable cosmic winter that will last forever, a final darkness from which nothing will ever emerge. This isn't science fiction or philosophical speculation. It's the inescapable conclusion that emerges when you follow the laws of physics to their logical endpoint. The same nuclear processes that make stars shine also guarantee their death. The same expansion that separates galaxies will eventually isolate them beyond any hope of contact. The same thermodynamic principles that organize matter into complex structures will ultimately reduce everything to cold, empty space. The timeline for this cosmic death is almost incomprehensibly vast. The final stars won't burn out for trillions of years, a period so long that the entire history of the universe so far represents less than 1% of the journey toward ultimate darkness. Human civilization, the formation of Earth, even the birth of our sun, are all recent events compared to the cosmic winter that awaits. But understanding this fate isn't about despair, it's about perspective. The temporary nature of cosmic light makes our current epoch extraordinary. We exist during the universe's brief, shining youth when stars are abundant, galaxies are forming, and complexity can emerge from cosmic chaos. We're witnessing the cosmic equivalent of a brilliant sunrise, even as we now understand that cosmic sunset is inevitable. The story of cosmic death begins with stellar birth. Every star is born with a finite fuel supply, burning hydrogen into helium through nuclear fusion. The most massive stars consume this fuel voraciously, living fast and dying young in spectacular supernova explosions. Smaller stars like our Sun burn more conservatively, but still face inevitable death when their fuel runs out. Even the tiniest red dwarf stars, capable of burning for trillions of years, will eventually exhaust their nuclear reserves. As stellar generations pass, the universe's capacity for creating new stars gradually diminishes. Each stellar death locks up material in stellar remnants, white dwarfs, neutron stars, and black holes, removing it from the cosmic recycling process that creates new generations of stars. The raw materials for star formation become increasingly scarce, leading to a gradual decline in cosmic brightness. The expansion of space adds another layer to this cosmic mortality. Driven by mysterious dark energy, the universe isn't just expanding, it's accelerating. This acceleration will eventually carry galaxies beyond each other's cosmic horizons, creating isolated island universes that can never again communicate or interact. The grand cosmic web of galaxies that we observe today will be torn apart by the inexorable growth of space itself. Even if some mechanism could halt stellar death and cosmic expansion, the laws of thermodynamics guarantee that the universe must eventually reach a state of maximum entropy. All useful energy will be dissipated as heat, all temperature differences will equalize, and all organized structures will decay. The cosmos will settle into a state of perfect thermal equilibrium where nothing can ever happen again. Yet within this seemingly grim cosmic forecast lies one of the most beautiful truths about existence. The temporary nature of cosmic structure makes our current moment extraordinarily special. We live during the universe's creative phase, when gravity can overcome expansion to build galaxies, when nuclear fusion can overcome gravity to power stars, And when chemistry can overcome thermodynamics to create the complex molecules necessary for life. Consider subscribing and hitting the thumbs up if you're fascinated by cosmic futures that challenge our deepest assumptions about permanence and change. And here's something to ponder. Knowing that all cosmic light is temporary, does this make our current moment more precious or more meaningless? Comment below with your thoughts. I'll pen the most thoughtful response. The journey toward cosmic darkness isn't a single event, but a series of transitions spanning timescales that dwarf human comprehension. First, the most massive stars will die, removing the brightest sources of cosmic light. Then medium-sized stars, like our Sun, will swell into red giants before fading into white dwarfs. Eventually, even the longest-lived red dwarf stars will exhaust their fuel, marking the end of normal stellar burning. After the stars die, stellar remnants will continue to evolve on even longer timescales. White dwarfs will slowly cool from white-hot to red to brown to black, taking billions of years to fade completely. Black holes will gradually evaporate through Hawking radiation, with the largest black holes taking longer than 10,100 years to disappear entirely. The ultimate fate of cosmic darkness depends on physical processes that operate on timescales so vast they challenge human imagination. If protons are unstable, as some theories suggest, then even the remnants of dead stars will eventually decay into radiation and elementary particles. If protons are stable, these remnants might persist indefinitely as cold, dark monuments to a universe that once blazed with stellar fire. But perhaps the most profound aspect of cosmic death is what it reveals about the nature of time and existence. The universe we observe today, filled with light and structure and complexity, represents just a brief flicker in an infinite expanse of cosmic darkness. Yet this flicker contains within it everything we know and love, every sunset, every star, every possibility for consciousness and creativity. Understanding cosmic death transforms our perspective on cosmic life. The stars aren't just distant suns. They read temporary beacons marking the universe as brief departure from its natural state of cold emptiness. Galaxies aren't permanent fixtures, but fleeting islands of organization in an ocean of expanding space. Life itself isn't a cosmic imperative, but an extraordinary accident that briefly illuminates the darkness. As we embark on this exploration of cosmic mortality, we all discover that the death of the universe isn't a single catastrophe, but a slow fade spanning timescales that make geological epochs seem like heartbeats. We'll witness the gradual exhaustion of stellar fuel, the dissolution of galaxies, and the ultimate victory of entropy over order. Yet we'll also find that this cosmic twilight contains its own strange beauty, a final chapter in the universe's story that is as inevitable as it is profound. The darkness that awaits isn't empty but pregnant with meaning, representing the ultimate destiny of space, time, matter, and energy themselves. Now let's begin our journey toward the cosmic winter, where we'll discover that understanding universal death illuminates the extraordinary nature of universal life. Chapter 1. Stellar Mortality. To understand why the universe will eventually go dark, we must first comprehend the life cycles of stars, the primary sources of cosmic light, whose inevitable deaths will gradually extinguish the cosmos. Stars are not eternal beacons, but mortal objects with finite lifespans determined by the fundamental physics of nuclear fusion and gravitational collapse. Every star begins its life in the same way. A massive cloud of hydrogen gas undergoes gravitational collapse, heating up until nuclear fusion ignites in its core. This moment of stellar birth marks the beginning of a cosmic battle between two fundamental forces. Gravity tries to crush the star inward, while the outward pressure from nuclear fusion tries to blow it apart. For most of a star's life, these forces remain in perfect balance. But this balance is temporary because nuclear fusion consumes fuel. Stars convert hydrogen into helium in their cores, gradually depleting their energy source. The specific lifetime of each star depends critically on its mass, creating a cosmic irony. The most massive stars that shine brightest also die fastest, while the smallest, dimmest stars live longest. Consider our own Sun, a medium-sized star with a total lifetime of approximately 10 billion years. It has been burning steadily for about 4.6 billion years and will continue for another 5 billion years before exhausting its core hydrogen. During this main sequence phase, the Sun maintains relatively stable luminosity and size, providing the steady energy source that makes life on Earth possible. However, when the Sun's core hydrogen becomes depleted, stellar evolution accelerates dramatically. Without nuclear fusion to provide outward pressure, the core begins contracting under its own gravity. This contraction heats the core, eventually triggering hydrogen fusion in a shell around the inert helium center. The energy from shell burning causes the Sun's outer layers to expand enormously, creating a red giant star with a diameter larger than Earth's current orbit. During its red giant phase, the Sun will be both larger and more luminous than today, but its surface temperature will be much cooler, giving it a reddish color. This phase represents stellar old age, a period of instability and dramatic change that ends when the star sheds its outer layers into space, creating a beautiful planetary nebula while leaving behind a hot, dense white dwarf star. White dwarfs represent one possible endpoint of stellar evolution. These stellar remnants are roughly the size of Earth, but contain nearly the entire mass of the original star, making them incredibly dense. A teaspoon of white dwarf material would weigh several tons on Earth. White dwarfs begin their existence extremely hot, often hotter than the original star's surface, but they no longer generate energy through nuclear fusion. Instead, white dwarfs slowly cool over billions of years, radiating away their stored thermal energy. They transition from white-hot to yellow to red to brown, eventually becoming completely dark objects called black dwarfs. The cooling process is extraordinarily slow. Even after 13.8 billion years of cosmic history, no white dwarf has yet cooled enough to become a true black dwarf. The universe simply isn't old enough yet. Massive stars follow dramatically different evolutionary pathways that lead to even more exotic endpoints. Stars more than 8 times the mass of the Sun burn through their fuel much more rapidly, living for only millions of years rather than billions. These stellar giants generate energy so voraciously that they quickly progress through multiple phases of nuclear burning, creating increasingly heavy elements in their cores. When a massive star exhausts all possible nuclear fuel, gravitational collapse becomes unstoppable. The core temperature rises to billions of degrees, but even this extreme heat cannot initiate further fusion reactions. In less than a second, the stellar core collapses from Earth-sized dimensions to a sphere only 20 kilometers across, creating temperatures and pressures that existed nowhere else in the universe since the Big Bang. This catastrophic collapse triggers a supernova explosion, one of the most violent events in the cosmos. For a brief period, a single supernova can outshine an entire galaxy containing 100 billion stars. The explosion scatters most of the star's material into space, enriching the interstellar medium with heavy elements created during the star's lifetime. However, the core collapse leaves behind either a neutron star or a black hole. Neutron stars represent matter compressed to nuclear density, where protons and electrons are crushed together to form neutrons. A neutron star contains more mass than the Sun compressed into a sphere only 20 kilometers in diameter. These objects spin rapidly and emit beams of radiation from their magnetic poles, appearing as pulsars when these beams sweep across Earth like cosmic lighthouses. The most massive stars undergo core collapse so extreme that not even neutron degeneracy pressure can halt the gravitational crushing. These stars form black holes, regions of space-time where gravity becomes so strong that nothing, not even light, can escape. Black holes represent the ultimate victory of gravity over all other forces, creating cosmic regions that are literally black because no light can emerge from within their event horizons. Each type of stellar death removes light from the universe in different ways. White dwarfs gradually fade as they cool, taking billions of years to become completely dark. Neutron stars emit some radiation, but far less than normal stars, and they too will eventually cool and fade. Black holes trap light entirely, creating regions where stellar mass exists but produces no observable radiation. The stellar mass function reveals a cosmic truth that accelerates universal darkening. Most stars are small red dwarfs with masses less than half that of the Sun. These stars burn their fuel so slowly that they can continue nuclear fusion for trillions of years. However, their individual light output is extremely low, hundreds of times dimmer than the Sun. The bright stars that dominate cosmic illumination are also the shortest-lived. This creates a cosmic evolutionary timeline where the universe's brightest phase occurs relatively early in its history. The most massive luminous stars have already lived and died multiple times over during the 13.8 billion years since the Big Bang. Medium-sized stars like the Sun are in their prime now, but will begin dying in billions of years. Only the small red dwarfs will continue burning into the far future, gradually inheriting a cosmos of fading light. Star formation rates throughout cosmic history reveal another crucial aspect of stellar mortality. The universe reached its peak star formation rate roughly 10 billion years ago, when gas was abundant and galaxy formation was most active. Since then, star formation has been steadily declining as successive stellar generations convert hydrogen into heavier elements and deplete the raw materials needed for new star birth. Each stellar death locks up material in stellar remnants, removing it from the cosmic recycling process. Gas that falls into black holes disappears entirely from the observable universe. Material in white dwarfs and neutron stars becomes gravitationally bound in such dense objects that it is unlikely ever to participate in new star formation. The universe's capacity for creating new stars diminishes with each stellar generation. Modern astronomical surveys allow us to observe stellar death in action across the cosmos. We can see white dwarf stars cooling in nearby galaxies, neutron stars spinning down as they age, and supernova explosions marking the violent deaths of massive stars. These observations confirm that stellar mortality is not a distant theoretical concern, but an ongoing process that has already begun reducing cosmic brightness. The Gaia Space Telescope has measured the motions and properties of over 1 billion stars in our galaxy, revealing stellar populations of different ages and evolutionary stages. This stellar census shows that many of the brightest stars we observe today are already in advanced stages of evolution, well on their way toward eventual death. The cosmic lights are already beginning to dim. Understanding stellar mortality reveals that the beautiful night sky we observe represents a temporary phase in cosmic evolution. Every star we see is burning finite fuel reserves, following evolutionary pathways that lead inevitably to darkness. The bright galaxies visible in deep space photographs show us stellar populations in various stages of life and death, capturing different moments in the universal transition from light to darkness. This stellar perspective transforms how we view cosmic time and cosmic change. The stars aren't permanent fixtures, but temporary residents of space, briefly illuminating the darkness before fading away forever. Their deaths aren't cosmic tragedies, but natural conclusions to stellar lives, part of the universal story that began with stellar birth and will end with cosmic darkness. Chapter 2: Galactic Dissolution. While individual stellar deaths mark the beginning of cosmic darkening, the ultimate fate of entire galaxies reveals an even more profound truth about universal mortality. Galaxies themselves are not permanent structures, but temporary collections of stars and gas destined for dissolution through multiple cosmic processes that operate on increasingly vast timescales. Our own Milky Way galaxy contains roughly 400 billion stars held together by gravity in a magnificent spiral structure spanning 100,000 light-years. This seems like a permanent, stable system, but galactic evolution reveals that even such massive structures face inevitable destruction through gravitational interactions, stellar evolution, and the expansion of space itself. The most immediate threat to galactic stability comes from galaxy collisions and mergers. Despite the vast distances between galaxies, they move through space under mutual gravitational attraction, sometimes leading to spectacular cosmic crashes that completely reshape galactic structure. Our Milky Way is currently on a collision course with the Andromeda Galaxy, and this merger will fundamentally alter both galaxies in approximately 4.5 billion years. Galaxy mergers aren't the gentle collisions you might imagine. When two large galaxies approach each other, their gravitational fields begin interacting billions of years before the galaxies actually touch. These tidal forces distort the spiral arms, trigger bursts of star formation, and fling stars into elongated orbits that stretch far beyond the original galactic boundaries. During the Milky Way-Andromeda collision, most stars will survive the merger itself, since the distances between individual stars are so vast that direct stellar collisions remain extremely unlikely. However, the gravitational chaos will completely disrupt the ordered structure of both galaxies, creating a new elliptical galaxy that astronomers have nicknamed Milkomeda. The beautiful spiral arms that characterize both galaxies will be destroyed forever. But galactic mergers represent only the beginning of galactic mortality. Even after galaxies merge into larger, more stable structures, they face inexorable dissolution through stellar evolution and the gradual depletion of star-forming materials. Each stellar generation converts hydrogen into heavier elements, slowly exhausting the fuel needed for new star formation. The process of galactic chemical evolution follows predictable patterns that lead inevitably towards stellar death. In the early universe, galaxies contained primarily hydrogen and helium, the light elements created during the Big Bang. The first generation of stars formed from this pristine material, living and dying to create heavier elements like carbon, oxygen, and iron. Subsequent stellar generations formed from gas enriched with these heavier elements, allowing more complex stellar structures and longer stellar lifetimes. However, this enrichment process also gradually depleted the hydrogen fuel needed for continued star formation. With each stellar generation, galaxies become less capable of forming new stars to replace those that die. Current observations reveal that galactic star formation rates peaked roughly 10 billion years ago and have been declining ever since. The universe is already past its stellar prime, transitioning from an era of vigorous star formation to a more quiescent phase dominated by stellar evolution and death. Most galaxies today form new stars much more slowly than they did in the past. The Hubble Space Telescope and other instruments have documented this cosmic transition by observing galaxies at various distances and therefore various epochs in cosmic history. Distant galaxies, seen as they appeared billions of years ago, show much higher star formation rates and more chaotic, irregular structures. Nearby galaxies appear more mature and organized, but also less active in forming new stars. This galactic evolution timeline predicts that star formation will continue declining until it eventually ceases entirely. Current estimates suggest that significant star formation will persist for perhaps another trillion years, but at ever-decreasing rates. Eventually, galaxies will exhaust their remaining gas supplies and become unable to form new stars to replace those that die. The expansion of space introduces another mechanism for galactic dissolution that operates on even larger scales. Driven by mysterious dark energy, the universe isn't just expanding, but accelerating. This acceleration will eventually overcome the gravitational forces that hold galaxy clusters together, isolating individual galaxies in an expanding ocean of empty space. Currently, the local group of galaxies, including the Milky Way, Andromeda, and about 80 smaller galaxies, remains gravitationally bound despite cosmic expansion. However, more distant galaxies are already being carried away by accelerating expansion, gradually disappearing beyond our cosmic horizon. In the far future, even nearby galaxy clusters will be torn apart by the relentless growth of space. This cosmic acceleration creates a hierarchy of dissolution timescales. First, the largest structures, superclusters of galaxies, will be stretched apart by expansion. Then, galaxy clusters will dissolve as their member galaxies are carried beyond mutual gravitational influence. Eventually, even binary galaxy systems will be separated by accelerating expansion, leaving individual galaxies as isolated islands in an ever-expanding cosmic ocean. The fate of isolated galaxies depends on their internal dynamics and stellar evolution. Without fresh gas supplies from intergalactic space or neighboring galaxies, star formation will gradually cease as existing reserves become depleted. The galaxy will transition from a star-forming system to a collection of aging stellar populations burning through their remaining fuel. Stellar dynamics within isolated galaxies also contribute to long-term dissolution. Gravitational interactions between stars gradually change their orbits, sometimes flinging stars completely out of the galaxy in a process called evaporation. Over timescales of 1,019 years, roughly half of a galaxy's stars will be ejected into intergalactic space through these gravitational encounters. The remaining stars in evaporating galaxies will gradually spiral inward toward the central supermassive black hole through a process called relaxation. As stars lose energy through gravitational interactions, their orbits decay, eventually leading them to be consumed by the black hole or ejected from the galaxy entirely. After roughly 1,020 years, most galactic stellar populations will have either fallen into the central black hole or been flung into intergalactic space. Black holes themselves play crucial roles in galactic dissolution. Most galaxies contain supermassive black holes millions or billions of times more massive than the Sun. As stellar material falls into these black holes, it releases enormous amounts of energy that can heat and expel the remaining gas from the galaxy, further reducing its capacity for future star formation. The process of black hole feeding also creates jets of high-energy particles that can extend far beyond the galaxy, carrying away material and energy that might otherwise contribute to continued galactic evolution. These active galactic nuclei represent the galaxy's transition from a star-forming system to a black hole-dominated remnant. Even the supermassive black holes that mark galactic cores face eventual dissolution through Hawking radiation. According to quantum mechanics, black holes slowly evaporate by emitting particles, with smaller black holes evaporating faster than larger ones. A supermassive black hole with 1 billion solar masses will take roughly 1,087 years to evaporate completely, but this process is inevitable given sufficient time. The timescales for complete galactic dissolution stretch far beyond current cosmic age. The universe is currently 13.8 billion years old, but galactic evaporation requires periods measured in quintillions of years. These numbers are so large they read difficult to comprehend. The current age of the universe represents less than 1/trillionth of the time required for complete galactic dissolution. Yet, despite these vast timescales, the process has already begun. Stellar evolution is already changing galactic properties, removing the most massive and luminous stars. Star formation rates are already declining from their peak values billions of years ago. Cosmic expansion is already isolating galaxy clusters, and preparing for the eventual dissolution of larger-scale structure. Observations of galaxy evolution provide direct evidence for these dissolution processes. We can see galaxies at various stages of stellar evolution, from young, star-forming irregulars to old, quiescent ellipticals dominated by aging stellar populations. We can observe galaxy mergers in progress, witnessing the destruction and reformation of galactic structure in real time. Understanding galactic dissolution reveals that even the largest, most stable structures in the universe face inevitable mortality. The beautiful spiral galaxies that populate our cosmic neighborhood represent temporary configurations of matter and energy, destined for eventual dissolution through stellar death, gravitational evaporation, and cosmic expansion. This galactic perspective adds another layer to cosmic mortality, showing that darkness approaches not just through individual stellar deaths, but through the gradual dissolution of the very structures that organize stars into coherent systems. The cosmos is transitioning from an era of galactic construction to an era of galactic destruction, marking another step toward universal darkness. Chapter 3. Accelerating Expansion. The discovery that cosmic expansion is accelerating represents one of the most profound revelations in modern cosmology, fundamentally altering our understanding of the universe's ultimate fate. This acceleration, driven by mysterious dark energy, ensures that the cosmos will not only go dark through stellar death, but will also face a more dramatic dissolution as the very fabric of space pulls apart all cosmic structure. The story of accelerating expansion begins with observations of distant supernova in the late 1990s. Two independent research teams were studying Type Ia supernova stellar explosions that serve as standard candles because they all reach roughly the same peak brightness. By comparing the apparent brightness of these supernovae with their known intrinsic luminosity, astronomers could determine their distances with unprecedented accuracy. What these teams discovered contradicted all expectations. Instead of finding that cosmic expansion was slowing down due to gravitational attraction between galaxies, they found that expansion was speeding up. Distant supernovae appeared dimmer than predicted, indicating they were farther away than expected in a decelerating universe. The cosmos was not only expanding but accelerating its expansion. This acceleration requires a form of energy that works opposite to gravity. Instead of attracting matter together, it pushes space apart. Astronomers call this mysterious component dark energy, and it appears to comprise roughly 70% of the universe's total energy density. Unlike matter and radiation, dark energy maintains constant density even as space expands, providing a steady driving force for continued acceleration. The implications for cosmic structure are profound. For the first 7 to 8 billion years after the Big Bang, matter dominated the universe's energy budget, and cosmic expansion gradually slowed as gravity worked to pull structures together. This allowed galaxies and galaxy clusters to form through gravitational collapse. However, as the universe expanded and matter became more diluted, dark energy's influence began to dominate. Once dark energy took control roughly 6 billion years ago, cosmic expansion began accelerating. This acceleration doesn't just affect the motion of galaxies, it fundamentally changes the nature of space itself. Regions of space that are not gravitationally bound together will be carried apart by accelerating expansion, eventually moving away from each other faster than light can travel between them. This creates cosmic horizons that will shrink over time rather than expand. Currently, we can observe galaxies at distances corresponding to roughly 46 billion light-years due to the expansion that has occurred while their light traveled to reach us. However, accelerating expansion ensures that distant galaxies will eventually be carried beyond our cosmic horizon and will fade from view entirely. The process of cosmic horizon shrinkage follows predictable patterns. Galaxies currently visible at large distances will gradually become more redshifted as their recession velocities increase due to acceleration. Their light will shift from visible wavelengths through infrared and radio, eventually becoming too weak and too redshifted to detect with any conceivable instrument. Eventually, these distant galaxies will cross what cosmologists call the Rindler horizon, the boundary beyond which objects recede faster than light and can never again send signals that reach us. Once a galaxy crosses this horizon, it effectively disappears from our observable universe forever. The information about its existence becomes causally disconnected from our local region of space. Current models predict that within roughly 100 billion years, the only galaxies visible from Earth will be those currently bound within our local group, primarily the Milky Way, Andromeda, and their satellite galaxies. The rest of the observable universe, containing billions of other galaxies, will have been carried beyond our cosmic horizon by accelerating expansion. This cosmic isolation has profound implications for future astronomers. Observers living in the far future will see a universe containing only their local galaxy cluster surrounded by apparently empty space. They will have no direct observational evidence that billions of other galaxies once existed. The cosmic web of large-scale structure that currently characterizes the universe will have been erased from their observable cosmos. The acceleration also affects smaller-scale structures, though on much longer timescales. Galaxy clusters that are not currently gravitationally bound will be torn apart as accelerating expansion overcomes their mutual gravitational attraction. This process has already begun for the largest structures in the universe and will gradually work its way down to smaller scales. Even gravitationally bound systems face eventual dissolution if acceleration continues indefinitely. While objects like our local group of galaxies will remain bound for the immediate cosmic future, continued acceleration could eventually overcome even strong gravitational bonds. In extreme scenarios, acceleration might become so powerful that it tears apart galaxies, stellar systems, and eventually even atomic structures. This ultimate fate is called the Big Rip, a cosmological scenario where accelerating expansion becomes so extreme that it overcomes all fundamental forces. If dark energy density increases over time rather than remaining constant, the Big Rip could occur in as little as 20 billion years. However, current observations suggest that dark energy density remains roughly constant, making the Big Rip unlikely with our current understanding. More probable scenarios based on constant dark energy density predict a different but equally dramatic fate. Accelerating expansion will continue indefinitely, gradually isolating all gravitationally bound structures into cosmic islands surrounded by ever-expanding voids. These islands will evolve independently, following their internal stellar evolution while losing all contact with the broader cosmos. The physics driving cosmic acceleration remains deeply mysterious despite decades of investigation. Dark energy might represent the energy density of empty space itself, what physicists call vacuum energy. Alternatively, it might be a new type of field that fills space and drives expansion, similar to the inflaton field thought to have driven cosmic inflation in the universe's earliest moments. Some theories propose that dark energy is not a new component, but a modification to our understanding of gravity itself. Perhaps Einstein's theory of general relativity breaks down on cosmic scales, requiring new physics that naturally produces accelerating expansion. These modified gravity theories attempt to explain cosmic acceleration without invoking mysterious dark energy. Regardless of the underlying mechanism, observations consistently confirm that cosmic acceleration is real and ongoing. Multiple independent measurements, including supernova observations, cosmic microwave background radiation, and large-scale structure surveys, all point to the same conclusion. Space is expanding at an accelerating rate that will continue for the foreseeable future. The discovery of cosmic acceleration fundamentally changed cosmologists' predictions about the universe's ultimate fate. Before this discovery, The main question was whether expansion would continue forever or eventually reverse into a big crunch. Accelerating expansion makes a big crunch impossible and guarantees that the universe will continue expanding and cooling indefinitely. This guaranteed expansion has profound implications for cosmic evolution. Star formation will eventually cease as gas becomes too diluted to collapse gravitationally. Existing stars will burn out without replacement, gradually darkening the cosmos. Even after stellar death, accelerating expansion will separate stellar remnants from each other, creating an increasingly empty and cold universe. The thermal history of an accelerating universe also differs dramatically from previous models. In a decelerating universe, matter and radiation cool as space expands, but the cooling rate decreases over time as expansion slows. In an accelerating universe, the expansion rate increases, potentially leading to faster cooling and more rapid approach to absolute zero temperature. Current measurements suggest that dark energy density remains roughly constant as space expands, providing steady acceleration without dramatic changes in expansion rate. However, even modest acceleration, sustained over cosmic timescales, produces enormous cumulative effects. The universe 100 billion years from now will be vastly larger, emptier, and colder than today's cosmos. Understanding accelerating expansion reveals that cosmic darkening involves not just the death of light sources, but the fundamental restructuring of spacetime itself. The universe isn't simply running out of fuel, it's actively growing larger and emptier, pulling apart the very foundations of cosmic structure and ensuring that even if new light sources somehow appeared, they would be isolated beyond any possibility of illuminating distant regions of space. This expansion-driven isolation represents a form of cosmic death that's more profound than simple stellar exhaustion. It's the death of cosmic connectivity, cosmic communication, and cosmic coherence. The transformation of a universe filled with interacting structures into a collection of isolated fragments drifting apart in an ocean of ever-expanding emptiness. Chapter 4. Heat Death. Beyond stellar death and cosmic expansion lies an even more fundamental fate that governs the ultimate destiny of the universe: the inexorable march toward maximum entropy, commonly known as heat death. This thermodynamic endpoint represents the final equilibrium state where all useful energy has been dissipated, all temperature differences have been eliminated, and no organized activity can ever occur again. The concept of heat death emerges from the second law of thermodynamics, one of the most fundamental principles in physics. This law states that the entropy of any isolated system tends to increase over time until it reaches maximum possible entropy. Entropy measures the degree of disorder in a system, and the second law essentially says that organized energy spontaneously transforms into disorganized heat, but never the reverse. You can observe this principle in everyday life. Hot coffee cools to room temperature by transferring heat to its surroundings. The organized thermal energy of the hot coffee becomes distributed throughout the environment, increasing overall entropy. Never do you observe room temperature coffee spontaneously heating up by extracting thermal energy from its surroundings, even though this wouldn't violate energy conservation. Applied to the entire universe, the second law of thermodynamics predicts that all organized energy will eventually be converted to heat and uniformly distributed throughout space. Stars burn by converting nuclear fuel into radiant energy, which eventually gets absorbed by matter and re-radiated as lower energy thermal radiation. This process irreversibly increases cosmic entropy while decreasing the universe's capacity for future organized activity. The timescale for universal heat death depends on the specific mechanisms by which entropy increases. Stellar burning represents one major pathway, converting organized nuclear fuel into disorganized radiation. But stars represent only a temporary phase in cosmic evolution. Their lifetimes are finite, and their fuel supplies are limited. Once all stars have burned out, the universe will need alternative mechanisms to continue its march toward maximum entropy. After stellar death, the primary entropy-producing processes will involve the gravitational interactions and eventual decay of stellar remnants. White dwarf stars will slowly cool by radiating away their thermal energy, taking roughly 1,015 years to reach the background temperature of space. Neutron stars will follow similar cooling patterns, but over somewhat different timescales, due to their different internal structure and composition. Black holes introduce fascinating complexities to the thermodynamic fate of the universe. According to Stephen Hawking's theoretical calculations, black holes possess temperature and entropy, with smaller black holes being hotter than larger ones. A black hole with the mass of our Sun would have a temperature of roughly 107 Kelvin, far colder than the current cosmic microwave background temperature of 2.7 Kelvin. This means that stellar mass black holes are currently absorbing energy from the cosmic background radiation rather than emitting it. They will continue growing slowly until the universe expands and cools enough that their Hawking temperature exceeds the background temperature. Only then will black holes begin net evaporation, slowly shrinking as they emit Hawking radiation. The evaporation process is extraordinarily slow for stellar mass black holes. A black hole with the mass of our Sun would take approximately years to evaporate completely, a timescale so vast that it makes the current age of the universe seem like an instant. Supermassive black holes containing millions or billions of solar masses would take even longer, requiring periods approaching 10,100 years for complete evaporation. During their slow evaporation, black holes will dominate the universe's energy budget and entropy production. They will be the primary source of activity in a cosmos otherwise devoid of energy-generating processes. The universe will transition through what cosmologists call the black hole era, when these slowly evaporating objects provide the only source of new entropy production. The final evaporation of the last black holes will mark a crucial transition point in cosmic evolution. Once all black holes have disappeared, the universe will contain only elementary particles, photons, and perhaps dark matter particles distributed throughout ever-expanding space. These particles will continue to interact occasionally, but the rate of interactions will decrease as cosmic expansion dilutes their density. Even after black hole evaporation, the approach to heat death will continue through increasingly rare and exotic processes. If protons are unstable, as predicted by some theories in particle physics, they will eventually decay into lighter particles and radiation. The predicted proton lifetime is roughly 1,034 years, far longer than the age of the universe, but still finite on cosmic timescales. Proton decay would represent the final dissolution of ordinary matter, converting the atoms that make up planets, stellar remnants, and any surviving complex structures into elementary particles and radiation. This process would eliminate the last vestiges of organization from the cosmic era when stars and galaxies dominated the universe's structure. However, even proton decay doesn't represent the absolute endpoint of thermodynamic evolution. In a universe containing only elementary particles and radiation, quantum fluctuations can still produce occasional interactions and particle creation events. These processes occur at extraordinarily low rates but continue indefinitely, slowly driving the universe toward ever higher entropy states. The quantum vacuum itself possesses energy and can spontaneously create particle pairs through virtual fluctuations. In the far future, when the universe is cold and empty, these quantum processes might become the dominant source of activity. Random quantum fluctuations could occasionally produce more complex structures, though the probability of such events becomes vanishingly small. Some theoretical calculations suggest that given infinite time, quantum fluctuations might eventually produce organized structures purely by chance. Random fluctuations could spontaneously create regions of lower entropy, potentially even forming new planetary systems or biological structures. However, the timescales for such events are unimaginably vast periods that make black hole evaporation seem rapid by comparison. The concept of heat death also depends on the ultimate geometry and fate of space itself. If the universe continues expanding forever, as current observations suggest, then thermal equilibrium will be reached at a temperature approaching absolute zero. All matter and energy will be distributed throughout infinite space, creating a state of maximum entropy at minimum temperature. Alternative cosmic scenarios could produce different thermodynamic endpoints. If cosmic expansion eventually reverses into a big crunch, the universe would heat up rather than cool down, potentially reaching a state of maximum entropy at very high temperature rather than very low temperature. However, current observations of accelerating expansion make this scenario extremely unlikely. The discovery of dark energy complicates thermodynamic predictions about cosmic fate. Dark energy appears to maintain constant density even as space expands, potentially providing an infinite reservoir of energy that could prevent the universe from reaching true thermal equilibrium. However, dark energy density is distributed uniformly throughout space and cannot be concentrated to perform useful work. Some speculative theories propose that dark energy might eventually decay or change its properties, potentially releasing vast amounts of energy that could temporarily reverse cosmic cooling. Such scenarios remain highly speculative and depend on physics beyond our current understanding of dark energy and cosmic evolution. The approach to heat death reveals the temporary nature of all cosmic structure and organization. Stars, galaxies, planets, and life itself represent brief departures from thermal equilibrium, temporary eddies of organization in the universe's inexorable flow toward maximum entropy. The energy gradients that power stellar fusion, biological metabolism, and geological activity will all eventually dissipate into uniform heat. Yet the timescales involved in reaching heat death are so vast that they challenge human comprehension. The universe could sustain complex structure and even life for periods that are millions of billions of times longer than its current age. From a human perspective, the approach to heat death is so slow as to be essentially irrelevant to any conceivable future development. Understanding heat death provides the ultimate context for cosmic evolution and the eventual darkness that awaits the universe. This isn't simply the extinction of light sources, but the fundamental elimination of energy gradients necessary for any organized activity. Heat death represents the final victory of entropy over order, the ultimate equilibrium from which no further change is possible. The thermodynamic fate of the universe reveals that cosmic darkness is more profound than the simple absence of light. It represents the end of cosmic activity itself, the final state where space contains only uniformly distributed matter and energy at thermal equilibrium. In this ultimate darkness, time becomes meaningless because nothing can ever happen to mark its passage. Chapter 5. Black hole dominance after stars die and galaxies dissolve. The universe will enter a remarkable epoch dominated by black holes, regions of space-time so extreme that they represent the ultimate victory of gravity over all other forces. These cosmic monsters will become the primary inhabitants of a dark universe, slowly evaporating through quantum processes while serving as the final sources of energy in an otherwise dead cosmos. Black holes form when matter becomes so compressed that its gravitational field prevents even light from escaping. The boundary of no return, called the event horizon, marks the point where the escape velocity equals the speed of light. Anything crossing this boundary, matter, energy, or information, becomes permanently trapped within the black hole's gravitational well. The formation of black holes occurs through several different mechanisms that operate throughout cosmic history. Stellar mass black holes form when the cores of massive stars collapse during supernova explosions. These stellar endpoints contain roughly 3 to 50 times the mass of our Sun, compressed into regions smaller than major cities, creating gravitational fields so intense that they warp space-time itself. Supermassive black holes, containing millions to billions of solar masses, lurk at the centers of most galaxies. Their formation mechanisms remain mysterious, but they likely grew from smaller seed black holes that formed in the early universe and subsequently accreted matter over cosmic time. These galactic monsters influence the evolution of their host galaxies through gravitational interactions and energetic outflows. Intermediate mass black holes, with masses between stellar and supermassive categories, may form through various exotic processes, including the direct collapse of massive gas clouds or the merger of smaller black holes. Recent gravitational wave detections have revealed the existence of black holes in this intermediate range, suggesting that black hole formation spans a continuous spectrum of masses. As the universe evolves toward darkness, black holes will gradually consume much of the remaining matter through accretion and direct consumption. Stars that venture too close to black holes will be torn apart by tidal forces, with their material forming hot accretion disks before spiraling into the black hole. This process releases enormous amounts of energy, making accreting black holes among the most luminous objects in the universe. However, the rate of black hole feeding decreases dramatically as stellar populations die out and galaxies become isolated by cosmic expansion. Once stars stop forming and existing stars burn out, black holes will have fewer opportunities to grow through accretion. The universe will transition from an era of black hole growth to an era of black hole dominance without significant feeding. During this black hole era, these objects will become the universe's primary source of activity and energy production. According to quantum mechanics, black holes are not perfectly black but emit faint radiation through a process called Hawking radiation. This emission occurs because quantum vacuum fluctuations near the event horizon can produce particle pairs, with one particle escaping while its partner falls into the black hole. Hawking radiation gives black holes an effective temperature that depends inversely on their mass. Smaller black holes are hotter and radiate more intensely than larger ones. A black hole with the mass of our Sun would have a temperature of roughly 10 to 7 Kelvin, while a supermassive black hole containing 1 billion solar masses would be 1 trillion times cooler. The extremely low temperatures of astronomical black holes mean they currently absorb energy from the cosmic microwave background rather than emitting net radiation. The universe must expand and cool significantly before black holes begin net evaporation. Current estimates suggest this transition will occur when the cosmic background temperature drops below each black hole as Hawking temperature. Once evaporation begins, black holes will slowly shrink as they radiate away their mass energy. The evaporation rate accelerates as black holes become smaller and hotter, creating a runaway process that culminates in explosive final evaporation. A solar mass black hole will take roughly 1,067 years to evaporate completely, while supermassive black holes require periods approaching 10,100 years. These evaporation timescales are almost incomprehensibly vast. To put them in perspective, the current age of the universe is roughly 1.4 times 1,010 years. A solar mass black hole's evaporation time is longer than the current cosmic age by a factor of 10^57, a number so large that it exceeds the estimated number of atoms in the observable universe. During their slow evaporation, black holes will dominate cosmic evolution in multiple ways. They will be the primary source of new entropy production, gradually converting their organized mass energy into random thermal radiation. They will also be among the few remaining sources of high-energy particles and radiation in an otherwise cold, empty universe. The distribution of black hole masses creates a hierarchy of evaporation timescales that will structure cosmic evolution. Smaller black holes formed through exotic processes in the early universe would evaporate first, followed by stellar mass black holes, then intermediate mass black holes, and finally supermassive black holes. The universe will experience a sequence of black hole populations disappearing as their evaporation timescales are reached. Primordial black holes, if they exist, could have masses ranging from microscopic to stellar scales. Those with very small masses would have already evaporated through Hawking radiation, potentially providing observable signatures that astronomers could detect today. Slightly larger primordial black holes might dominate the dark matter budget and could be evaporating throughout cosmic history. The evaporation process itself produces fascinating theoretical complications. As black holes shrink, their Hawking temperature increases, causing them to radiate more intensely. The final moments of black hole evaporation release enormous amounts of energy in extremely short time frames, potentially creating the most energetic events in cosmic history outside of the Big Bang itself. Black hole evaporation also raises profound questions about information conservation in quantum mechanics. If information that falls into a black hole is destroyed when the black hole evaporates, this would violate fundamental principles of quantum theory. The black hole information paradox remains one of the deepest unsolved problems in theoretical physics. Some proposed solutions to the information paradox suggest that Hawking radiation carries subtle correlations that preserve fallen information, allowing it to be recovered in principle from the radiation spectrum. Other solutions propose that black holes don't completely evaporate, but leave behind stable remnants that preserve the fallen information. These theoretical questions could have profound implications for cosmic evolution. The merger of black holes represents another important process during the black hole era. As cosmic expansion separates most structures, gravitationally bound black hole systems will continue to evolve through orbital decay driven by gravitational wave emission. Binary black holes will slowly spiral together over vast timescales before merging in catastrophic events that release enormous amounts of energy in gravitational waves. Recent detections of gravitational waves from black hole mergers provide direct evidence for these processes and allow us to study black hole physics in unprecedented detail. Future gravitational wave observatories will monitor black hole mergers throughout cosmic history, providing insights into how these extreme objects evolve and interact over cosmic time. The late-stage universe dominated by evaporating black holes will be a strange place where quantum effects become cosmologically significant. The typical energy scales will be extraordinarily low, but occasionally, black hole evaporation will produce high-energy particle bursts that briefly illuminate regions of otherwise empty space. These events will become increasingly rare as larger black holes require longer evaporation times. Black hole thermodynamics also provides insights into the fundamental nature of entropy and information. Black holes possess entropy proportional to the area of their event horizons rather than their volumes, suggesting deep connections between gravity, quantum mechanics, and information theory. Understanding these connections might reveal new physics relevant to cosmic evolution. The black hole era will span timescales that dwarf all previous epochs of cosmic history combined. During this period, black holes will serve as the universe's primary inhabitants, slowly converting their mass into radiation while providing the only significant sources of energy and activity in an otherwise dead cosmos. Their eventual evaporation will mark another major transition in cosmic evolution. When the last black hole finally evaporates, the universe will transition to a new phase characterized by elementary particles and radiation distributed throughout ever-expanding space. This transition will mark the end of the black hole era and the beginning of the final approach to heat death, when only quantum fluctuations disturb the cosmic equilibrium. Chapter 6. Proton Decay. Even after black holes have evaporated and left behind only elementary particles scattered through expanding space, the universe may face one final dissolution, as the very atoms that comprise ordinary matter slowly decay into radiation. Proton decay represents the ultimate dismantling of atomic structure, converting the stable matter that forms planets, stellar remnants, and any surviving complex objects into pure energy and fundamental particles. Protons are among the most stable particles known to physics. In our current understanding, they form the nuclei of hydrogen atoms and serve as essential building blocks for all heavier atomic nuclei. The prediction of proton decay emerges from grand unified theories, GUTS, that attempt to unify the electromagnetic, weak nuclear, and strong nuclear forces into a single fundamental interaction. These theories suggest that at extremely high energies, the distinctions between these forces disappear, and they become different aspects of a single underlying force. Grand unified theories require new physics beyond the standard model of particle physics, including the existence of very massive particles that can mediate proton decay. These hypothetical particles, with masses near the grand unification scale of 1016 GeV, are far too massive to produce in any conceivable particle accelerator. However, they could facilitate rare processes that allow protons to decay into lighter particles. The most commonly predicted proton decay mode involves the conversion of a proton into a positron, anti-electron, and a neutral pion, which subsequently decays into photons. This process would violate baryon number conservation, a symmetry that is preserved in all known particle interactions, but could be broken by grand unified interactions operating at extremely high energy scales. Experimental searches for proton decay have been ongoing for decades, using massive detectors containing thousands of tons of material and monitoring for the characteristic signatures of proton decay events. These experiments have not yet detected any convincing evidence for proton decay, but they have established lower limits on the proton lifetime that exceed 1,034 years for most decay modes. This lower limit on proton lifetime is already extraordinarily long compared to any other timescale in physics. The current age of the universe is roughly 1.4 times YY years, making the proton lifetime at least 1,024 times longer than the entire cosmic history so far. Even if protons do decay, this process is so slow that it has negligible effects on current cosmic evolution. However, given infinite time in an ever-expanding universe, even processes with such extraordinarily low probabilities will eventually affect every proton in the cosmos. If the proton lifetime is 1,034 years, then after roughly 1,036 years, most protons in the universe will have decayed into lighter particles and radiation. The decay of protons would mark the final dissolution of ordinary atomic matter. Stellar remnants like white dwarf stars and neutron stars, which consist primarily of protons and neutrons, would slowly disintegrate as their constituent particles decay. The atoms that make up any surviving planets, asteroids, or complex structures would similarly decompose over cosmic time. This process would be extremely gradual from any local perspective. Individual proton decays would occur randomly throughout matter, occasionally releasing small amounts of energy, but not significantly, affecting the bulk properties of objects for vast periods. However, accumulated over timescales of YP years, proton decay would completely eliminate all atomic structure. The energy released by proton decay would provide a faint source of radiation and otherwise cold, empty universe. Each decay event produces roughly 1 GeV of energy in the form of particles and photons. While this is tiny compared to stellar energy production, it would represent the dominant source of new energy production in a post-stellar universe. Neutrons face similar theoretical instability through grand unified interactions. Though their decay modes and lifetimes may differ from those of protons, Free neutrons are already unstable, decaying into protons, electrons, and neutrinos with a lifetime of roughly 15 minutes. However, neutrons bound within atomic nuclei are stabilized by nuclear forces and could persist until grand unified decay processes become significant. The decay of bound neutrons in atomic nuclei would occur through similar mechanisms as proton decay, mediated by the same massive particles predicted by grand unified theories. Different grand unified models predict various relationships between proton and neutron lifetimes, but most suggest that both types of nucleons would decay on similar timescales. Neutron stars represent extreme environments where nuclear matter is compressed to extraordinary densities. The stability of matter in these objects against grand unified decay processes remains an active area of theoretical research. Some calculations suggest that the extreme conditions in neutron star cores might actually accelerate nucleon decay, while others propose that collective effects might provide additional stability. The implications of proton decay extend beyond simple matter dissolution. If protons decay, this would violate baryon number conservation and could have profound implications for cosmology and the matter-antimatter asymmetry observed in the universe. Understanding why the universe contains more matter than antimatter is one of the major unsolved problems in cosmology. Some theories propose that the same grand unified interactions responsible for proton decay might also explain why the universe evolved to contain more matter than antimatter during its early evolution. These theories, called baryogenesis scenarios, require violations of baryon number conservation similar to those that would enable proton decay. The search for proton decay continues to drive developments in experimental particle physics and detector technology. Underground detectors like Super Kamiokande in Japan and proposed future experiments like Hyper Kamiokande use thousands of tons of ultra-pure water, monitored by sensitive photomultiplier tubes, to search for the faint light signals that would accompany proton decay events. These experiments must operate deep underground to shield them from cosmic ray interactions that could mimic proton decay signatures. They require extraordinary sensitivity and stability to distinguish genuine proton decay events from the much more common background interactions caused by natural radioactivity and cosmic rayons that penetrate even deep underground locations. Alternative theories propose different mechanisms that could lead to proton instability. Some models involving extra dimensions suggest that protons might decay through interactions with gravitational effects in higher dimensional space. Other theories propose that protons might be composite particles that could dissociate under extreme conditions rather than decaying through fundamental particle interactions. The uncertainty in proton decay predictions reflects our incomplete understanding of physics at the highest energy scales. While grand unified theories provide elegant theoretical frameworks, they make predictions about energy scales that are far beyond current experimental reach. The grand unification scale is roughly 1,016 times higher than the energies accessible at the Large Hadron Collider. Even if protons are absolutely stable, other forms of matter decay might eventually eliminate organized structures. Complex nuclei could decay through various mechanisms, and even electrons might be unstable if certain exotic theories prove correct. The ultimate stability of matter remains an open question that will require both theoretical advances and improved experimental sensitivity to resolve. The timescales for proton decay, if it occurs, stretch far beyond the evaporation of even the largest black holes. While supermassive black holes might take 10,100 years to evaporate through Hawking radiation, proton decay would continue for periods measured in multiples of 1,034 years. This represents another vast extension of cosmic timescales beyond previous epochs. From a philosophical perspective, proton decay represents the ultimate victory of quantum uncertainty over classical stability. Even the most stable particles in nature might eventually succumb to quantum processes that operate over cosmic timescales. This suggests that no structure, no matter how stable it appears, can persist indefinitely against the random fluctuations of quantum mechanics. The discovery of proton decay, if it occurs, would provide crucial insights into the fundamental nature of matter and the unification of physical forces. It would confirm that even the most basic constituents of atoms are temporary phenomena rather than permanent features of reality. Understanding proton decay could revolutionize our understanding of particle physics and cosmology. Whether or not protons actually decay remains one of the great unanswered questions in physics. The resolution of this question will require continued experimental searches and theoretical developments over potentially decades or centuries. However, the possibility of proton decay illustrates how even the most stable aspects of physical reality might face inevitable dissolution over cosmic timescales. Chapter 7. Vacuum Decay. Beyond all previously discussed mechanisms for cosmic darkness lies the most catastrophic possibility: vacuum decay. This theoretical process could not only eliminate all existing structure in the universe, but could fundamentally alter the laws of physics themselves, creating a form of cosmic death so complete that it would erase even the possibility of future organization or complexity. The concept of vacuum decay emerges from quantum field theory and our understanding of how fields behave in empty space. What we perceive as empty vacuum is actually a seething foam of quantum fluctuations, with virtual particles constantly appearing and disappearing. The properties of this quantum vacuum determine many fundamental aspects of physics, including particle masses, force strengths, and the basic constants that govern natural law. Current physics suggests that our universe exists in what is called a false vacuum, a state that appears stable but may not represent the absolute minimum energy configuration possible for quantum fields. Just as a ball might rest in a shallow valley on a hillside, while a deeper valley exists elsewhere, our vacuum state might be merely locally stable, while a more stable true vacuum exists at lower energy. The distinction between false and true vacuum states has profound implications for cosmic stability. If our current vacuum is indeed false, then it is possible for quantum tunneling events to nucleate bubbles of true vacuum that expand at the speed of light, converting false vacuum regions to true vacuum as they propagate. This process would be irreversible and unstoppable once begun. The Higgs field, responsible for giving mass to fundamental particles, provides a concrete example of how vacuum stability issues arise. Measurements of the Higgs boson mass and the top quark mass suggest that the Higgs field might exist in a metastable state, stable against small fluctuations, but potentially unstable against large quantum fluctuations or high-energy perturbations. If the Higgs field underwent vacuum decay, the resulting true vacuum state would have different physical properties than our current universe. Particles might have different masses, fundamental forces might have different strengths, and the basic structure of atoms and molecules could be completely altered. Any complex structures that exist in our current vacuum state would be instantly destroyed. The nucleation of vacuum decay bubbles would begin as quantum fluctuation events occurring spontaneously in random locations throughout space. Quantum mechanics allows for the possibility that even very improbable events will eventually occur given sufficient time. The probability of vacuum decay in any given region might be extraordinarily small, but over cosmic timescales and cosmic volumes, such events become statistically inevitable. Once a vacuum decay bubble forms, it would expand at the speed of light, converting everything in its path to the new vacuum state. Observers inside the expanding bubble would be completely unaware of the approaching boundary until it reached them, since no signal can travel faster than light to provide advance warning. The transition would be instantaneous and absolute. The interior of a true vacuum bubble would be governed by completely different physics than our current universe. If particle masses changed dramatically, atomic nuclei might become unstable, causing all matter to disintegrate. If fundamental force strengths changed, stars might not be able to maintain stable fusion, or gravity might become too weak to hold galaxies together. Current calculations suggest that our vacuum state is at least metastable, meaning that small fluctuations cannot trigger decay. However, these calculations depend on our understanding of physics at energy scales far beyond current experimental reach. Discoveries of new particles or forces could dramatically change the vacuum stability analysis. The timescale for spontaneous vacuum decay remains highly uncertain, but could be extraordinarily long. Some estimates suggest that vacuum decay might not occur for periods exceeding 10,100 years, far longer than any other cosmic process. However, other calculations yield much shorter timescales, potentially as brief as billions or trillions of years. High-energy events could potentially trigger vacuum decay more rapidly than spontaneous quantum tunneling. Cosmic ray collisions, black hole evaporation, or other extreme astrophysical processes might create energy densities sufficient to destabilize the vacuum locally. Some theories suggest that the very early universe experienced vacuum transitions that drove cosmic inflation. The anthropic principle provides an interesting perspective on vacuum stability. If vacuum decay were common or rapid, complex structures like galaxies, stars, and life would never have time to develop. The fact that we exist to observe a stable universe might itself be evidence that our vacuum state is more stable than naive calculations suggest. Alternative theories propose that vacuum decay might not be catastrophic, but could instead drive transitions to new phases of cosmic evolution. Some models suggest that vacuum decay could create new regions of spacetime with different physical properties, potentially allowing for novel forms of organization and complexity that are impossible in our current universe. The multiverse concept introduces additional complications to vacuum decay scenarios. If our universe is part of a larger multiverse containing regions with different vacuum states, then vacuum decay might represent transitions between different pocket universes rather than absolute cosmic death. True vacuum bubbles might themselves be unstable against decay to even lower energy states. String theory and other advanced theoretical frameworks propose that vacuum states exist in vast landscapes of possible configurations, with different vacuum states corresponding to different sets of physical laws and constants. Vacuum decay might represent transitions between different points in this landscape rather than absolute termination of physical law. Experimental tests of vacuum stability remain challenging because they require understanding physics at energy scales far beyond current technology. However, precision measurements of particle properties, particularly the Higgs boson and top quark masses, provide indirect constraints on vacuum stability. Future collider experiments might probe higher energy scales and provide better constraints. Cosmic ray observations also provide some constraints on vacuum stability. The highest energy cosmic rays create particle collisions with energies far exceeding anything achievable in terrestrial laboratories. The fact that these natural high-energy events have not triggered vacuum decay provides evidence that our vacuum is at least stable against perturbations at these energy scales. The search for gravitational waves from vacuum decay represents another potential experimental approach. If vacuum decay bubbles were nucleating and expanding throughout the universe, they might produce detectable gravitational wave signatures. Current gravitational wave observatories have not detected such signals, providing additional constraints on vacuum decay rates. Vacuum decay scenarios highlight the fundamental uncertainty that pervades our understanding of ultimate cosmic fate. Unlike stellar death or black hole evaporation, which are consequences of well-established physics, vacuum decay depends on theoretical frameworks that remain speculative and untested. Our universe might be fundamentally stable, or it might face catastrophic decay at any moment. The philosophical implications of vacuum decay are profound. This process would represent not just the end of current cosmic structure, but the end of the physical laws that govern reality itself. Unlike other forms of cosmic death, vacuum decay would eliminate even the possibility of future development or organization under different conditions. From a thermodynamic perspective, vacuum decay might represent the universe's transition to an absolutely final state of minimum energy. While heat death involves the approach to thermal equilibrium within our current vacuum state, vacuum decay would transition the cosmos to a fundamentally different ground state from which no further evolution would be possible. The possibility of vacuum decay illustrates how cosmic evolution might face ultimate boundaries imposed by the fundamental structure of physical law itself. Even if all other cosmic death scenarios could somehow be avoided or reversed, vacuum decay represents a potentially unavoidable termination of cosmic history. Understanding vacuum stability remains one of the deepest challenges in theoretical physics, requiring advances in our understanding of quantum field theory, particle physics, and cosmology. The resolution of these questions will determine whether the universe faces merely local forms of cosmic death or absolute termination of physical reality itself. Whether vacuum decay actually threatens our universe remains unknown, but the possibility highlights how even the most fundamental aspects of reality might be temporary phenomena rather than eternal features of existence. Chapter 8. Quantum Eternity. Even after stellar death, galactic dissolution, black hole evaporation, proton decay, and potential vacuum collapse, the universe may not reach absolute stasis. Quantum mechanics suggests that perfectly empty space is impossible, and random quantum fluctuations could continue creating occasional bursts of activity and organization throughout infinite cosmic time, leading to a strange form of quantum eternity, punctuated by rare moments of spontaneous creation. The foundation of quantum eternity lies in the uncertainty principle, which states that energy and time cannot be simultaneously measured with perfect precision. This fundamental limitation allows quantum systems to borrow energy from the vacuum for brief periods, creating virtual particle pairs that appear spontaneously before annihilating each other and returning their borrowed energy to the quantum vacuum. These quantum fluctuations occur constantly throughout space, even in regions that appear completely empty. The vacuum buzzes with activity as virtual particles pop in and out of existence on timescales so brief that they cannot be directly observed. However, their collective effects produce measurable consequences, including the Casimir force between parallel plates and the Lamb shift in atomic energy levels. In the far future, when the universe has expanded to enormous scales and cooled to temperatures approaching absolute zero, quantum fluctuations will become the dominant source of activity. The thermal energy that currently masks quantum effects will have dissipated through cosmic expansion, leaving only the irreducible quantum foam that characterizes empty space. The rate of quantum fluctuations depends on the local energy density and temperature of space. In a cold, expanded universe, these fluctuations will be extremely rare, occurring perhaps once every 1,050 years in galaxy-sized volumes. However, given infinite time, even extraordinarily improbable events become inevitable through quantum tunneling and spontaneous symmetry breaking. One of the most remarkable predictions of quantum eternity involves the spontaneous creation of organized structures through random fluctuations. Statistical mechanics shows that any finite system will eventually fluctuate into any possible configuration given sufficient time. In principle, quantum fluctuations could spontaneously assemble complex structures, including planets, stars, or even living organisms. The timescales for such spontaneous assembly are almost inconceivably vast. The probability of quantum fluctuations randomly assembling even a simple bacterium is so small that the required waiting time exceeds 101,050 years, a number so large that it cannot be written in conventional notation. Yet quantum mechanics guarantees that such events will occur infinitely, often given infinite time. These spontaneous creations would be extraordinarily brief. Complex structures assembled by random fluctuations would almost immediately decay back to their constituent particles as the fluctuations that created them dissipate. A spontaneously created planet might exist for only fractions of a second before disintegrating, while smaller structures like molecules might persist for slightly longer periods. However, some spontaneous creations could potentially achieve temporary stability through lucky configurations of quantum states. A randomly assembled star might briefly ignite nuclear fusion, providing energy to maintain its structure for longer periods. Such events would create temporary islands of organization and activity in an otherwise dead universe. The most profound possibility involves quantum tunneling events that could spontaneously create entirely new regions of spacetime. Quantum mechanics allows for the possibility that vacuum fluctuations could nucleate new universes through processes similar to cosmic inflation. These baby universes might branch off from our dying cosmos, creating new regions with fresh supplies of energy and matter. The mathematics of quantum tunneling suggests that given infinite time, fluctuations will eventually occur that are large enough to overcome any energy barrier. Even barriers that seem absolutely insurmountable from a classical perspective become permeable over cosmic timescales through quantum tunneling effects. Some theories propose that our entire universe originated as a quantum fluctuation in a pre-existing vacuum state. If this is correct, then the spontaneous creation of new universes through quantum tunneling might be a natural and inevitable process that continues throughout cosmic evolution. Our dying universe might serve as the launching pad for countless new cosmic regions. The concept of eternal inflation, developed by cosmologist Alan Guth and others, suggests that quantum fluctuations in scalar fields can drive exponential expansion that creates infinite numbers of pocket universes. If eternal inflation is correct, then cosmic death in our local region might be balanced by cosmic birth in other regions, maintaining an eternal cycle of creation and destruction. Vacuum metastability adds another layer of complexity to quantum eternity scenarios. If our current vacuum state is unstable, quantum fluctuations might occasionally trigger transitions to different vacuum states with altered physical laws. These transitions could potentially restart cosmic evolution with different fundamental constants and particle properties. The landscape of possible vacuum states might contain regions that are more conducive to long-term stability and complexity than our current universe. Quantum tunneling between different vacuum states could eventually lead to cosmic evolution toward more stable configurations that support extended periods of structure formation and complex organization. Quantum field theory predicts that even the most fundamental particles might not be absolutely stable against quantum decay processes. Virtual particles emerging from vacuum fluctuations could interact with real particles in ways that cause them to decay or transform into different types of particles. These processes would operate on timescales far longer than proton decay, but can eventually affect even the most stable remnants of matter. The interplay between quantum fluctuations and gravitational effects introduces additional possibilities for spontaneous organization. Quantum fluctuations in the gravitational field itself might occasionally create regions of enhanced density that could gravitationally collapse to form new structures. These quantum gravitational instabilities could provide mechanisms for spontaneous star formation even in otherwise empty space. String theory and other advanced theoretical frameworks suggest that quantum fluctuations might access higher dimensional spaces beyond our familiar three spatial dimensions. Fluctuations that propagate through extra dimensions might be able to create effects in our observable universe that appear to violate conservation laws, but actually represent energy transfer from hidden dimensions. The measurement problem in quantum mechanics adds philosophical depth to quantum eternity scenarios. If consciousness plays a role in quantum measurement, as some interpretations suggest, then the spontaneous creation of conscious observers through quantum fluctuations might trigger fundamental changes in the functions, nature of physical reality itself. Decoherence theory provides a more conventional framework for understanding how quantum fluctuations might create classical structures. Even in a cold, empty universe, quantum systems can undergo decoherence through interactions with environmental fluctuations, potentially stabilizing random configurations into semi-permanent classical structures. The many worlds interpretation of quantum mechanics suggests that all possible quantum outcomes actually occur in parallel universes. From this perspective, quantum eternity represents not just the possibility of rare spontaneous events, but the guarantee that all possible structures and histories will be realized infinitely, often across the quantum multiverse. Information theory provides another perspective on quantum eternity. If information cannot be destroyed, as some interpretations of quantum mechanics suggest, then the information content of our current universe might persist indefinitely, even after all matter and energy have dissipated. This information might somehow influence future quantum fluctuations in ways that recreate organized structures. The holographic principle, emerging from black hole physics, suggests that all information in a region of space might be encoded on its boundary surface. In the far future, quantum fluctuations on cosmic horizons might recreate the information patterns of previous cosmic epochs, potentially resurrecting vanished structures in new forms. Quantum eternity scenarios illustrate how the apparent finitude of cosmic evolution might be illusory. While classical physics suggests that the universe faces inevitable heat death, quantum mechanics opens possibilities for continued activity and organization throughout infinite time. The death of the universe might represent not an ending, but a transition to a new mode of existence governed entirely by quantum uncertainties. Understanding quantum eternity requires grappling with mathematical infinities and conceptual paradoxes that challenge human comprehension. The interplay between quantum mechanics, thermodynamics, and cosmology in these extreme scenarios pushes the boundaries of theoretical physics and raises profound questions about the nature of existence, time, and possibility itself.